Welcome, everybody, and thank you for joining us for the virtual pub today, topic of image analysis. And it's my great pleasure to introduce our speaker for today. Tingying Peng joins us from the Helmholtz AI Center in Munich, where she is a group leader. Tingying has an undergrad degree in electrical engineering from Beijing University and a PhD in biomedical engineering from the University of Oxford. After her PhD, she was a postdoctoral researcher at the Technical University of Munich, and since 2020, she's been a Helmholtz group leader. Her group's goal is to create new AI methods to help life scientists and pathologists analyze microscopic images in a more qualitative and efficient way. And so we're really happy to have you here, Tingying, and please go ahead with your presentation and tell us about the recent work from your team.
Yeah, thank you, Johanna, for this nice introduction. Yeah, it's a great pleasure for your invitation and get this opportunity to present basically the tool we created which is supposed to help a biologist to analyze their data in more efficient and more in a more accurate quantification way. As Johanna mentioned, the title of my presentation is basically this BaSiCPy enables scalable and robust shading correction for optical microscope images. So before I go to the topic, I would also like to shortly introduce myself. So as Johanna introduced, I'm a junior group leader at Helmholtz AI. And then basically my group is working on develop AI method for different type of microscope images. So like bright field fluorescence, and 2Ds or 3D light sheet or quantum electrotomography. So quite a diverse image modalities. And there is also something special we deal with is this histopathology slice, which we use in the clinical settings for cancer diagnosis. So we are also doing that. So the group basically is two parts. The first one part is doing this AI for advanced microscope images. So all microscope images except a histopathology image. And the other half is working on computational pathology, so only pathology images. So there is a couple of examples, the tools I'm developing. The first is this illumination corrections, which I will go into it deeply. The second is this light sheet microscope. So we are in cooperation with Professor Helmholtz, and he's basically one of the inventor of this light sheet microscope. This is super nice, the light sheet, because it's much faster than confocal microscope, but you see this kind of stripes, which is because of tissue absorption. Then we develop something, use deep learning, actually on the Fourier space, use a graph neural network, we can get rid of the stripe. We also developed method to stitch the imaging together. So basically a couple of tools which is specialized in the for the light sheet microscope. We also have works on the quantum electrotomography. So you have this electrotomography, and then you have this kind of membranes, and which are super important. So we actually develop a tool for segmenting this membrane, which is called a membrane-seq. So if you just Google membrane-seq PyPy, you will get it. And then people use it to do the membrane segmentation for the quantum electrotomography. And we also have a tool to detect the proteins on the membrane. That one is currently in progress, but we have our last version, membrane V1, already published, so can be used. And we are currently in the stage of developing the second version. So the other half of the group is working on the computational pathology. Here, I also would like to show a few examples. The first example is this compactless batch effect. So we also have an observation of batch effect in the histopathology slice. If you see for different hospitals, the color of histopathology slice tend to be different. And imagine, if we train an AI method on one color or only on the data from one hospital, it may not working well for the other hospitals. So normally people do that while this color normalization. So the idea is you train your model on the hospital 1, and then if you apply to the hospital 2 and you want to turn the color of hospital 2 in the same color of hospital 1 and then apply to your model. But that's quite a fragile because the color basically normalization can also go wrong. And then you basically have a wrong slice as the input of the model. And then of course the output of the model won't be good. So instead of doing things on the output side, we would like to train the model from the beginning. So make sure the model is robust to different color variations. So we created the method as a kind of a color augmentation. So during the training, we already augment the data into different color. Then during the inference, when you apply, take the model, is already good. So at least in theory, the model should be robust to different colors. The second example is kind of self-supervised learning because, I mean, as we know, the machine learning or all the AI method need to have a lot of annotation, and that's a problem. And for pathologists or doctors, they don't have time to do it. So we have some kind of self-supervised learning. So basically, we combine the supervised information and self-supervised information, and then this can basically lower down the requirement of annotation amount. So basically, I mean, imagine before if you have to annotate, I don't know, maybe 1,000 cells. Now we only need to annotate like 100 or even like 20 or 50. So that's can accelerate the model training for quite a bit. And we also have more project which is close to the clinical settings. So this project I would like to highlight is to predict the microsatellite instability for colorectal cancer. So that's quite an important biomarker for colorectal cancer. So basically, we have this whole side image. Those are huge. Actually, this image, it's sometimes even one slice is equivalent to the whole ImageNet. Then we have to patch it into patches, and then we basically we train something called transformer and to aggregate the patch information into the final diagnosis. So whether the patient to predict whether the patient is microsatellite unstable or it's stable. That actually works quite nice. It's works on the resection. It's also work on the biopsy. That's actually the first time it's true. It's kind of very promising on the biopsy slice. So that's why it's get published in the Cancer Cell. We also have a huge amount of data, like multi cohort from all over the world. We also write articles about reproducibility. As we know, reproducibility is always an issue in biomedical studies. So in this kind of computational pathology sense, so we write some recommendations, published as a comment in the Nature Medicine last year. Actually, now it's 2 years before. So from getting the data, so to split the training and the testing data, and the pre-processing the data, and to develop model, and whether it's nice to publish the model, and the final evaluation, and also publication. So we are not only publish a paper, and for the community, it's nice to always publish the model weights so other people can use it, more or less out of box fashion. So that's about generally introduction of my group. So now we go to the topic of the tool I would like to focus on, which is this illumination correction. So basically, illumination correction, if you as we know, any optical microscope have these uneven illuminations. So if you stitch them together, you tend to have these grids. So my tool can actually get this into this, so which is super impressive. And this is of course because in each patch, because of the specimen is actually, the microscope is actually only focused on one part of specimen, because the specimen itself is too large to fit into the field of view. So then for each patch, the illumination is strong in the center and then weak in the corner. So you get this, and then when you stitch them together, you get this these grids. And it's also cause a problem for the stitching itself because of the gradient of this intensity gradient. Sometimes with the stitching, it doesn't work. If you can actually correct this, then you actually also don't have the stitching problem because stitching algorithm tend to be also stable. So this uneven illumination actually it's always a problem. I mean, it's known as a problem for a long time. So if you check the intensity in the middle of the image, it could be like twice as the intensity in the corner. If you do like cell segmentation, so for example, use traditional way at that time, I think that was Kevin published this in 2014. That's actually a bit before the deep learning come from. So at that time, if you use like traditional cell segmentation, then the cell area could be even 4 times of the cell in the corner, which is basically this amount of error go to the quantitative analysis. So traditionally, one can also correct this using some kind of reference slice. For example, like this kind of calibration slice, which give you a uniform, or which at least is supposed to give you uniform signal. And then if you take a picture of this, you get like something like this, and that's exactly a flat field. And you would like to divide your image by this flat field. And there is also something called dark field. That's basically the offset of your microscope. Then you basically first subtract your dark field and then divide your flat field, and that's your corrected image. However, this prospective method have problems. First, you need to find out how to calibrate your images. And second, you have to do it every time before you do your experiment, because if somebody else do the experiment, for example, change the wavelength or something, use another camera or something, and that's actually have different flat field. So that's the ideal case. One have to measure a flat field or do the calibration every time before they run experiment. So that's certainly tedious. That's why according to the survey of Kevin Smith at 2014, so 10 years ago, only 40% of the biologists, they do it, or they are aware to do it. I mean, it's even not guaranteed they all do it in a like. So that's obviously a problem. And that's why people now people are trying to propose a retrospective method. So which means we don't need this slice anymore. We just get our image and we try to estimate this flat field and dark field from the image directly and then do the correction. So there is no extra work for the biologist on their side. Something related is this kind of time lapse. So besides this special like this uneven illumination in space, you can see also like this background. I don't know. Yeah, you can see like this. There is also a background of fluctuations. So at the beginning of the movie, and then because of medium reflecting light, they tend to be very, very bright. And as you go on the movie, and because of fountain bleaching, and then they become more like more dark, and basically that's actually affect the quantification. So actually, the signal you are getting is not only come from the foreground, but also come from the background. That could actually mess up your quantification. Later, I will show you why is the case. So we developed our method, which is called BaSiC, published in Nature Communication in 2017. That method itself is based on something called low rank and the sparse decomposition. So I won't go through the details of how it works, but I can show you an example, like then give the like how to say the intuition why it works. So this low rank and sparse decomposition is used for video decomposition, foreground and background decomposition. And so on the left side is basically the normal videos, and the low rank part is basically all the static objects in the video, so which is mostly like background. And then on the sparse part, and that's actually the foreground, so the people or the moving, basically the moving object, which is mostly like the people who are moving. So if you also have one person which is standing all the time there, then they also go to row rank. And that's exactly the idea we are using for our algorithm, because we observe this kind of flat field and the dark field is the same for every patch, because that's how the microscope collects your image. So for shooting, every patch is the same flat field and dark field. So since they are repetitive, so they actually go to the row rank part, where the signal is not the same, because you are moving on the specimen, and the signal you get for each patch is different. So they become the sparse. So they become the sparse component. So through this thing, we can actually decompose the flat field and dark field in the low rank and get a signal from the residue. And we do the same thing for the background bleaching. So if you have like an image like this, you have like this super frustration background, and we can actually estimate a background per image and then it's corrected. So the details of that are quite complicated. I mean, are a bit more complicated, so I won't go to too much details. So basically we use this kind of minimization of sparse minimization, which we use something called low related L1 norm, but that's technical details. And we also want our estimate flat field to be smooth, because we know usually for microscope, the flat field should be more or less smooth. And here we use Fourier transform and make sure it's sparse at the Fourier domain, because sparse in the Fourier domain is equivalent to smooth in the image domain. So that actually all works very nicely for the microscope image. It's also work on the time lapse. So if you see the quantification on the raw image, like if you just put like this yellow box and quantify the intensity within the yellow box that I got used from Fuji, and that's the curve you got if you do it on the raw image. And only after the correction, you get the real signal, because you see the cells are coming out. So there should be more signal than less signal. And now you get the real nice and accurate quantification. So we actually also apply that in real experiment. So this blood stem cell differentiation. So the blood stem cell differentiates into this GM lineage, which is like a white blood cell, and the MEG lineage, which is a red blood cell, and at like this lineage differentiation point, and you can see an upregulation of this CD1632 onset. And that's, you can only see it after this basic correction. So if you don't do the correction, and it's just a super random signal you get from the raw data. And for the MEG lineage, you at like this marker onset, you don't see the upregulation, because the red curve is the after correction. And that's also in the final quantification. If you don't do any correction, you don't actually see the difference of this molecular amount fluorescence in this two lineage. Only after correction you see like this upregulation Q1 in the GM lineage as compared to the MEG lineage. So you see the statistic difference. So basically that highlights the importance of using the illumination correction. So it's not only make your image looks better or more beautiful, it's actually affect your quantification. So at that time we wrote BaSiC as a Fuji plugin, and it still exists, so one can really use it. And we actually get a lot of contact users, both in academic and in industry. It's also cited by other pipelines, such as Dennis MC Micro, which is a toolbox specialized for multiplexing imaging processing. And BaSiC is basically the first module of MC Micro. Basically, the first thing you do is to get rid of to even the illumination, and then do the stitch and do the analysis quantification and etc. So it's also cited widely. So we are happy to show people cite us because people use our tool, not because people have a better method. In the AI field, and because it's enormous competition, usually people cite a baseline method to show their method is better. But that's not the case. I mean, because illumination correction is still quite a narrow field. So people cite us because they are using the method. We also approached by a few companies, such as this Akuya Bioscience. So they do multiplexing. So they would like to incorporate the algorithm into their commercial software, and a few others. But over the time, we also realized BaSiC is also nothing is perfect. BaSiC is also not perfect. Sometimes it do have problems. So one particular thing we observe is BaSiC actually fears if your movie have a high correlated foreground, such as these movies. So you can see like the cells, they differentiate, they become bigger, or they have more cells, but they always stuck in the same place because of median, because it's easy for them to track. And then here, if you use this BaSiC as to estimate flat field, and then you actually got a hotspot in your flat field. And that's also not very surprising because you consider like the algorithm of BaSiC, it doesn't know this place is more bright on average. It's because uneven illumination, or is because there is more cell gathering there. So the BaSiC doesn't know. That's why it's tend to use the cell signal in the flat field, or take the cell signal as the uneven illumination. The same thing go to the 3D, because for 3D, we know like from Z slice, you have some kind of continuity. So that means you have a high correlated slice around the Z. And that's also cause problem for BaSiC, because it's highly correlated and the BaSiC cannot deal with it. So if you have this image, you do the BaSiC correction, you can still see there is not like you don't get rid of the stripes, or you don't get rid of the grades perfectly. And we check like that's the basic flat field, and you can see it's like every other, it's like most of other flat fields. If you take a glass, it seems it works fine. But if you look at the image more closely, you see actually the uneven illumination is actually on the bottom of the image. So you can feel it's like at the bottom, or especially at this corner, it's like super bright, and then the basic flat field is actually not taking care of that. So we actually develop a BaSiCPy. So basically the second version of BaSiC. So first it's in Python. So it's easy to use. So original BaSiC is in Fuji, so which is means Java, and it's also available in MATLAB. But the new one is purely in Python, so it's can also integrate with the Napari. So we have the BaSiCPy version as well as a Napari plugin. And we also did a few critical algorithm improvements, such as we now have some kind of segmentation mask to deal with the problem, to overcome the problem of correlated images. So we can restrict our estimation of flat field either in the foreground or in the background. So for these movies, so now we know, okay, the foreground are somehow correlated, so we would like to get rid of the foreground. We only estimate the flat field from the background, and now we don't have a spot problem anymore. So now the BaSiCPy estimate flat field is pretty good. So it doesn't have this hotspot result from the clouded cells. And we also do it with a 3D light sheet microscope. Here we actually restrict the estimation in the foreground, because for light sheet, there is no background. So the background is always zero, or is close to zero, not too much information in the background. And then we get the flat field. Our new flat field is actually reflect better the truth. And if you stitch the result with the segmentation mask, and you don't see these grades, so the grades basically disappear, or at least it's much better than before. So the Python implementation, we also did it in JAX. So it works on the GPU and the CPU, and also TPU. And because of the fact we did it in GPU and JAX, and compared to the original ImageJ plugin, one can get like 20 to 15 times acceleration, so which is super nice because that means it can use on the larger scale image processing. Which is particularly favored by this high throughput images. And we have this Fuji plugin, which I have already talked about. And we also did a small tweaking of the optimization, so make it more stable. And we have this segmentation mask to solve the correlated foreground issue, which I already also talked about. And the last but not least, we also have a auto-tune, like parameter auto-tuning strategy. And this is super nice in practice because the communication we got previously for BaSiC, a lot of communication is like how to set up the parameters, because we have some parameter to adjust how smooth your flat field should be. And then this sometimes can be tricky in practice. So sometimes, like, we also know, like, the biologists, they got the wrong result because they set up the wrong parameter, or they find it's tedious to set up the parameters, because sometimes they have like these high throughput multi-view things, and they want to do the correction per view, and then it's like a lot of images. So they have to set up the parameter for each view, and that's super difficult in practice. So now this auto-tune strategy, and we can actually solve the problem. So you just call in the algorithm without worrying about how to set up the parameters. So it works on 2D as the original BaSiC, but much quicker. It works on the 3D. That's something like the original BaSiC haven't shown. For the time lapse, it also works on this correlated time lapse movies. And that's also a very nice example to show like this correction is super important. If you see, if you don't do the corrections, and then the mean intensity you get from the region A is actually even higher than region B. Even the region B is actually the patch which have cells. So that's clearly not correct. And after you do the correction, and at the beginning of movie, because there's only stem cells, there's no cells come out, and it's the same, close to 0. And then after you have cells, then your foreground patch, the mean intensity of foreground patch begin to increase. And it also get rid of this kind of background oscillations. So the quantification is now much more smooth and stable. So this is another example we apply for this bacteria live imaging time-lapse data. So uncorrelated images basically everywhere tend to give you some different result. And only after correction, you see this nice two peak, one is control, one is with this some kind of drug. And our collaborator also compare with other tools such as Elastic, and basically it doesn't work very well. So they are quite happy, like actually basically solve the problem. So we already released the BaSiCPy on the internet, so under the MIT license, so it's entirely free, and it's available by PyPy, and we're happy to see the monthly download is already 500. That's a quite impressive number for us, because we checked a few other famous software in the bioimaging community, such as Cell Profiler, is also 500. I mean, a bit more than us, but it's not way more than us. And you understand, for the behind the Cell Profiler is basically a team. And behind BaSiC, it's basically, I mean, we have our main developer, Yasuki, who is a very bright Japan postdoc who work at the Nikon Institute in Japan. It's basically him and me, so two people, and I don't mainly do coding, so I answer questions. Sometimes they have special question about parameters and whether it works or not, but like all the coding is on Yasuki himself. So even with that, we are like achieve similar download as Cell Profiler, so we are quite happy and also proud of ourselves. And people are also comment on BaSiCPy. So we got a Gary V's lab wrote a blog about the BaSiCPy. I mean, at that time it's called PyBasic. And then compare to other illumination correction software, so cell profiler, like I have to admit the illumination correction module in the cell profiler is super simple. It's basically take the mean of the images and then do some kind of smoothing, which is not as sophisticated as BaSiCPy. And the CIDR, which is published like in this 2014, a bit before the BaSiCPy, is based on also optimization, but in general, it's also not super stable as the BaSiCPy. So there is a few advantage of BaSiCPy. For example, it's generally need less image to calculate the effective illumination correction function as compared to the cell profiler and the CIDR. It works on different images, so multiplexing, time lapse, and whatever. And it's also super robust to noise and artifact. And we also provide examples, so they are reasonably easy to transfer to your own problem. So the two cons he was mentioned, currently not well funded as cell profiler. I said cell profiler have a team behind it. We only have 2 persons. Currently, we are writing this CZI open science grant. So hopefully, if we got funded, then we can have the funding to hire a postdoc on that for 2 years, or hire a software engineering for 2 years. Then basically we get much stronger support on the support to the community. Because sometimes we also notice people are comment on the issues on the GitHub. Sometimes if we have time or we just want to get the BaSiCPy manuscript, and then maybe we answer. And sometimes if we don't have time, then we also don't answer the questions. I have to admit. But if we get the funding for the software engineer, and then we can do this in a more regular fashion. So the other con he was mentioned is like the output images need to be corrected, but that's we had a new feature, so we actually solved out the problem. Now the BaSiCPy actually can output a corrected image as well, so you don't have to take an extra step to correct the image using the output flat field and dark field. So it do the correction for you. So, and they also concurrently choose the BaSiCPy because it's written in Python and a few nice things. So we are quite happy. So we also trying to finish our manuscript and submit to Nature Method, and hopefully that can also get more people aware of our tool and learn to use our tool. So that's basically the end. I'm very happy to take questions.